Hello, and welcome to our video on topic 4.5, application problems. Today we're going to be starting with our wind and water current problems. And in example 0, we want to think about a boat that has a top speed of 35 miles an hour, but is going in a river that has a current of 2 miles per hour. Well, if you are in the boat and you are going downstream or with the current, then relative to the land, you might be going faster because you've got the 35 miles per hour that the boat is going, plus the 2 miles per hour that the current is going, which gives you a rate relative to the land of 37 miles per hour. That means we're adding the boat speed with the current speed to get our total speed. However, if the boat is traveling upstream or against the current, then the speed relative to the land is going to be slower. So in this case, we have our boat speed at 35 miles per hour, but the current is slowing us down, so we have to subtract it. That means we would actually be going 35 miles per hour 33 miles per hour, didn't subtract right, relative to the land. So we're going to take our boat speed and subtract the current speed. And that's going to be our major concept for today. In today's lesson, we're going to be using our uniform motion formula that we've used previously during the year. And we want to recall that in uniform motion, we're going to be using rate times time equals distance. And in uniform motion problems, actually, we often use chart setup to help us, and we are going to do that again today. All right, so let's go ahead and look at some of our helpful hint for today's lesson. With wind and current problems, we want to look for keywords. When the speed is increased, we will think of a tailwind if we're in an airplane, a current if we're on the water, or thinking downstream when we're on water. If our speed is being decreased on a plane, we might hear the term headwind, and in the water, we would think against the current or going upstream. So common steps, right, just to recap, is that we want to start with our vehicle. So I'm jumping down here because it's going to be the faster speed. And then we either want to add or subtract the wind or the current based on whether we're against or with it. So again, if we're against in number 1, in an airplane, we would call that a headwind, and we would subtract the wind. With the wind is called a tailwind, and we would add the wind speed. And then if we have a boat problem, against the current or going upstream, we're subtracting, and with the current or downstream, we're adding. All right, so let's jump into our first problem. We have a cabin cruiser, which is a boat, is traveling with the current, and it went 60 miles in 3 hours. Against the current, it took 5 hours to travel the same distance. Find the rate of the cabin cruiser in calm water. All right, so I am going to start by organizing my information into a chart where we have rate times time equals distance. And in this case, I'm going to think about, we've got with the current and against the current. And those are going to be my 2 categories or rows. So I'm going to make a row of with and to make a row of against. So, as we talked about in example 0, with the cabin cruiser going with the current, let's just say that the cabin cruiser has a rate. Now again, we wouldn't always define our variables here because we're going to do that in the chart as well. But just to understand where these are coming from, the x is going to be my cabin cruiser speed, and the y is going to be my current speed. So with, the rate is going to be faster because the current is helping. When we're against the current, our rate relative to land will be slower because the current is slowing us down. Now in this case, we have different times given that with the current it took 3 hours, and so I'm going to go ahead and fill that in, and against the current it took 5 hours, and it gave us the distance of 60 miles. Well, you might be tempted to put the 60 in the distance column, and that would make sense. But when we use a chart, we always want to remember that that third column should be an algebraic expression. It's just a good habit, and it's going to help us set up our equations. So what we're going to do is we're going to think, oh, well, the distance algebraically is 3 times the quantity of x plus y, and that's got to equal the distance that was given in the question. So our first equation is going to be 3 times the quantity of x plus y is equal to 60. And our second equation would be 5 times the quantity of x minus y, also equal to 60. So just as a side note, in these types of questions, you could also have the same time given, but different distances. So don't think that it's always going to be, oh, they have the same distance and different times. I also want to mention that in previous problems, when we've had round trip problems like this, we've set the distances equal to each other. But notice, we have 2 unknowns and therefore need 2 equations in order to solve. So again, in algebra, when we have 1 unknown, we can solve in 1 equation, but if we have 2 unknowns, we need 2 equations. So I am just going to move this one down just a, oops, I missed the mark just a little bit. I'm going to try to move this down just a little bit because what we want to do is divide, rather than distribute the 3 into the quantity of x plus y and distribute the 5 into the quantity of x minus y, I can divide out the numbers 3 and 5 and make my equations easier to work with. So now I have x plus y equals 20 and x minus y equals 12. Well, oh my goodness, we have opposite coefficients with the y variable, so it's super easy to solve by elimination. Now, of course, if you use substitution, it will come out correct, but isn't it easy here just to add the equations together and get 2x equals 32? So when we divide by 2, we get x is equal to 16. That's all they asked us for in this question, was the speed of the cabin cruiser, or the x. So I'm just going to write that answer. 16 miles per hour. But if they asked us for the current speed, it would be very simple to plug that back into either one of these equations to get that the rate of the current is actually 4 miles per hour. So that would be pretty easy to do. All right, so now we're going to transition to our next problem, which is a miscellaneous problem, which is really geometry related. And whenever I have a geometry type of problem, I like to draw a diagram to help me. So I'm going to do that here because when I read this, it sounds a little confusing. The sum of the perimeters of 2 squares is 68 inches. If 2 times the first square's edge length is added to thrice the second square's edge length, the result is 41 inches. Find the area of each square. So I see 2 squares and I think, well, I'm going to draw or make two squares. So I've got my first square, and now I'm going to go and make another one. Now I don't know if these are to scale. I don't know which one's bigger, but I'm making the second one bigger, and we'll find out whether I was right at the end. But I don't know the edge of either one of these squares. So I'm going to say that the edge of the first square is x, and the edge of the second square is y. So I have two unknowns. I have two squares, and I don't know the side length or the edge of either. Now, the first sentence says the sum of the perimeters of two squares is 68 inches. Well, I know that the perimeter of a square is adding up the four sides, which are all the same. So the perimeter of the red square is 4x, and the perimeter of the blue square is 4y, because there's four sides and each of them are a length of y. So I can make an equation based on what I highlighted in yellow. The sum of the perimeters of two squares is 68 inches. That would be 4x plus 4y equals 68. So that's my first equation. Now remember, two unknowns, I must have two equations. So let's go ahead and look at the next line. If 2 times the first square's edge length, I'm going to stop right there, 2 times the first square's edge length, well, that would be 2 times x, right? Because we defined x as our first square's edge length. Is added to, right, I'm back here, and we're going to be is added to. Well, added to means that we're going to be using an addition sign. Thrice the second square's edge, well, that's just a really fancy way to say 3 times the second square's edge. So 3 times the second square's edge, the second square had an edge of y, so 3 times that would be 3y. The result is 41 inches. So I'm just going to go back to my yellow highlighter and say is 41 inches. So my first equation comes from the sum of the perimeters of two squares is 68 inches. And the second equation comes from that second sentence, which is kind of long, but I broke it down into 3 parts. 2 times the first square's edge length, 2x, is added to plus thrice the second square's edge, that's 3y. The result is 41 inches. So that's equals 41. Awesome. Now we have 2 equations, 2 unknowns. The hard work is done. Let's go ahead and use elimination to see if we can transform the second equation by multiplying by -2, and we can eliminate the x. Again, not the only way to solve this. You also might have noticed there's a common factor of 4 in the first one. So you could have even divided by 4 and then used substitution. So let's see, 41 times 2 is going to be -82. When I add these together, the x gets eliminated and I get -2y is equal to -14. So when I divide by -2, I get the y is 7. I can plug that back into either equation, so I'm going to plug it into the second one, 2x plus 3y, but I'm replacing the y with 7 that I just found. And then when I subtract 21 from 41, I get 20, and divide by 2, and I'm going to get x is equal to 10. So I know my edge length now. I know that the x is equal to 10. So I didn't do this to scale, did I? Because I made the red one look smaller when in fact it should be the bigger one. And the final question, it says, find the area of each square. Well, area of a square is just going to be the side length squared, so x squared. So that means this would be 100 square inches. And the blue one, again, its area would be y squared, and we know now that the y is equal to 7. So 7 squared is 49 square inches. Okay, so that concludes our video on day one word problems for systems.